Welcome everyone. So in this video we are going to talk about simulation and also one of the techniques to perform simulation, which is known as inverse transform method. So before we go into what is simulation, what is inverse transform method, so we just do some revision on what is a distribution. Okay, so in this page that you see on the screen now is actually a normal distribution with means 0.1, standard deviation 0.1. So in the table here, columns B to D, there are 300 numbers generated. So the X here is basically 300 numbers from normal distribution of mean 0.1, standard deviation 0.1. And column D is basically illustrating or indicating what is the probability that X is less than lowercase of x. So a standard notation, uppercase is referring to the random variable, small x here is referring to the number or the values here. So in this case, this is basically indicating that, okay, so what is the probability that x is less than or equal to 0.23940, given that x, capital X, is following normal, capital X is following normal distribution with mu 0.1, sigma 0.1. Okay, so that is what we have in the first line. Okay, but bear in mind one thing, because this is a spreadsheet illustration, so you can see that actually the number of decimal is more than 5. So you have more than 5 decimals here. Okay, of course I do a formatting here and to illustrate or to demonstrate to show only 5 decimal or 5 digits after the decimal. Okay, so in order to find out what is column D, of course you can use some software like Python, R, or any software that has some statistical package in it. And of course you can also use like normal table, that what we learned in high school or secondary school mathematics. Okay, so what we learn here, or what we are looking at here, is something elementary in the probably like probability, year 1 probability or statistics subject. So of course we have not encountered how do we use spreadsheet to compute the CDF. Okay, so here this is a CDF, right? So CDF is it stands for cumulative density function. Okay, now for column D here, the CDF, using spreadsheet, also one thing to take note here is that you may observe that I'm not using Microsoft Excel in this video. I'm using WPS Office or WPS spreadsheet in to be more precise here. Okay, so you can use any software like LibreOffice, OpenOffice, Microsoft Excel. The function could be probably similar. I'm under Linux environment now, so I do not have Microsoft Excel to demonstrate to you, but using the WPS spreadsheet is good enough, because this video is not going to teach the Excel techniques, but it's going to introduce what is this simulation, inverse transform technique, and also some of the scenario why we need to do these kind of things. Okay, so in other videos I will be demonstrating how do we use Microsoft Excel to handle this kind of or to perform simulation. So I will put the links to the other videos in the description. Okay, so now back to here, we can actually given that this is a normal distribution, we can compute the CDF easily by using norm dist. So the function that you will be using, depending on what type of spreadsheet software you are using, will be similar if they are not the same. Okay, so elementary mean is 0.1, standard deviation is 0.1, so it's basically the x and then mu sigma. Okay, then the last one is 1 or 0, basically to return cumulative or CDF or PDF, cumulative density function or probability density function, right? So you can put 1 or 0 here, or true, false here, also okay. So I will be using 1 here. I won't go into details of what is this argument, so you can play around with that with your own spreadsheet. Okay, so now you can see that we successfully recreate or recover the columns that we deleted earlier using this formula, right? So if you are using normal table, you can use normal table look up what is the CDF one by one. So there are few different approaches, but over here, this channel, this video, we will be focusing on spreadsheet software. Okay, so now that is a normal distribution, right? So given X, you can find out what is the probability that is less than X. Okay, so same thing that we can actually do is the log normal distribution. Given the X, what is the probability of X less than or equal to X? Okay, so that is CDF. Of course, over here you can also delete, I mean, we can delete this column and then we perform the same thing. Let me delete one more time. We can use the log normal distribution and then the number, the mu and sigma. Okay, and then you can see that we get the same number as well as like what we have previously. Okay, so you can take note here is that this worksheet versus this one, the column D is the same. Okay, of course the X is different because we are looking at different distributions. So the first one we are looking at normal distribution, the second one is log normal distribution. So of course you have many others distribution that you can actually, given the X, find the CDF, given the X, find the CDF, and so on, right? So we won't be able to illustrate every distribution, but with these two distributions, it's a good introduction. Now the simulation, the inverse transform technique is basically saying that, okay, instead of given X to find column D, now if I'm given column D, how do I find column C, right? So for example, if I delete this one, how do I find out what is the value of X given 0.91834? So again, if you are using normal table, in this case, you can use normal table to find out the X, right? But that is what we learned in high school. So over here, we are going to look at how do we perform this thing and why do we need to do these kind of things. Okay, right? So moving on to the next tab here. So now if we want to say that, okay, given the normal distribution, what is the random given a number here, we want to find out the normal distribution, right? So just like this case here, given column D, you want to find out column C. So I just reverse the column. So column D is now column C is located here, and this is located here. So you can see that the numbers are the same. Okay, so the headers of the column, I change it to RAND, close, open and close the bracket, is because this is the function that you can actually use to generate random number from 0 to 1. Okay, so this RAND function will generate random number, random variable of uniform distribution from 0 to 1. Okay, of course we are talking about continuous uniform distribution 0 to 1. Okay, so you can see that every time I type in something, press enter, the value changes. So if I run this thing, I recalculate this thing for 1000 times, so I get 1000 random variable from uniform distribution from 0 to 1. Okay, so this is basically one of the techniques that you can use. That means from a uniform distribution, we want to convert it to like normal or log normal distribution. We will look at that later. Okay, so now if let's say you start with a blank one, if I want to generate like for example 5 random numbers from uniform distribution, how do I do that? So I can actually type in equal random and then I get this thing, right? So you see I directly get 5 random numbers that is from 0 to 1. So this is uniform distribution. Okay. So a lot of software, they will have this kind of similar function built in. So in Excel, we use the function RAND. Okay, in VBA we use RND. So it's slightly different, but both of them gives you the same thing, random number from uniform distribution. So if you want to generate 1000 times of uniform distribution from 0 to 1, so you can just copy paste for 1000 row, then you get 1000 random variable. So that is actually a simulation. You can see that a process of simulation is basically that you want to repeat this process for a few times. Usually in practical sense, you won't be generating the number for 10 times practically. So we may run the simulation for 50,000, 100,000 times, or even more, depending on how complicated your model is, what is the processing power, and so on, how high the accuracy you need. Okay, so over here a 5 numbers is just for illustration purposes only. Okay, so you can see that simulation, the process is basically sort of like getting a random number from a distribution. Okay, it could be a multiple distribution. Okay, basically you want to get a number, or you want to simulate a situation. So over here we talk about a number. So when you talk about situation, that involves slightly more complicated scenario. For example, you want to model the financial statement. Okay, so the revenue is revenue is like between 1,000 to 10,000, let's say, uniformly distributed, and then your cost is like 500 to 9,000, and then you want to simulate the whole scenario. So that is basically very complicated. It involves a lot of modeling techniques, so we won't go into details here. So when we talk about generating random numbers simulation, it's just like you want to generate, for example, 10,000 uniform random number from uniform distribution. So a process of simulation is just like, for example, this one. So this is one number, right? So let me put it here. So I want to repeat for 10,000 times, then basically we can just go to the A 10,000, right? And then paste it here. So I have 10,000 random number from uniform distribution now. So this is a process of simulation of 10,000 times. But most of the time, you may not be using uniform distribution. So how do we convert uniform distribution to, like, for example, normal distribution? How do we do this conversion? So that involves the techniques inverse transform technique, okay, or inverse transform method. So that is what we are going to learn in this video. Okay, so let's go back to the spreadsheet or the example. So given this number, how do we find out that this is actually 0.2394? Okay, so let's go back to the normal distribution. So you can see that it's but like a reverse of the process only. So given column D, you want to find column C. So how do you get column D? You use uniform distribution from 0 to 1, right? So why we use uniform distribution from 0 to 1? Because CDF is also from 0 to 1, right? Because when you talk about CDF, it would be like greater than or equal to 0, less than or equal to 1. So that is the CDF. You won't have a number under a normal measure, right? So you won't have a probability that is negative value. Total probability cannot be more than 1 as well. So CDF is in correct. Same thing here, uniform distribution from 0 to 1 is also from 0 to 1, which is you can generate by using the RAND function or just a random variable. So again, one thing to emphasize here is that every software that they give you the random number, the RAND function or any random number, is actually called pseudo random. Okay, so pseudo random is basically like it is not really random but pseudo random. Okay, so because there is no way for you to generate a pure random numbers. Okay, so now with these two concepts linked together, we know that okay, I use uniform distribution, it's 0 to 1, CDF is 0 to 1. Then uniform distribution, I can generate the number easily, right? So from RAND techniques, or you can sort of like randomly say out a number 0.12345. I mean, that is not random enough, but it's random from this moment, right? So it's random number, so 0.34567. Okay, So that is a random number, and then use that random number saying that, okay, this random number is actually the CDF, and from the CDF you find back the X. So basically from here you want to find back here, and this part is actually 0 to 1. Okay, that is actually a very good way of viewing this thing. Okay, so now of course we can also plot a chart of this thing so that we see what is actually happening. So you may probably see this chart when you are taking the subject of simulation. Okay, right, so first thing, I don't really need this column. I just want to plot this CDF of these 300 numbers, right? So I can actually sort this number. Let me sort this number. Of course, again, this video is not on spreadsheet technique, so we will be okay, right, so we sort from smallest to largest, and then we can plot a graph of this thing, right? So a line chart. Let me find. Okay, again, this is not Microsoft Excel, so I'm not too familiar with some of the keyboard shortcut here as well. So because I seldom use spreadsheet program over here. Okay, right. So you can see that the chart is basically from about near to 0 to about near to 1, right? So quite nice here. And okay, we don't really need this one. And then let me do some formatting a bit here and there. Okay, format. Wait, format axis. Maximum is 1, right? Okay, and then say this is 0.1. Okay, this is better. Okay, right, so you can see that this is sort of like the CDF kind of thing, but this is empirical, of course. And how do I change the chart type? Okay, never mind. So we will keep it in this way. So you can see that this is like empirical chart, right? So now what we have here is basically saying that, okay, if I have a random number of 0.24, okay, so what is the X value that you have? Okay, so how do we get that? Over here we are illustrating this thing in 0.24. Okay, right, so I just basically want everything to be here. Okay, so how do we get that this is what is the X value for 0.24? You draw a horizontal line here, and then when it touches this CDF vertically down, then you can see what is the value of X, right? So now select data. So again, I can actually change the value of X here. Okay, right, so okay, so when you draw a horizontal line 0.24, let's say, so when it touches the CDF line, go vertically down, then you see what is the value. I mean, this is the graphical meaning of this kind of well, not meaning, graphical illustration of the inverse transform technique, right? So you draw a horizontal line, when it touches here, it goes down, then you will know what is the value of the X. Okay, so how do we illustrate this one? Basically, I just want to add one more line here, right? So let me just add one more line to illustrate this thing. right? So you can see that now I get a horizontal line that touches here, and when it goes down, then you can see that probably it is around, let's make this thing a bit larger. Right, so we are not talking about data visualization, how to make the chart looks nicer and so on. We just want to illustrate this thing. So it's about 0.02, near to about 0.029, right? So maybe 0.027. So let's see if we do the same thing. Can we do the same thing here? Right, so we can actually compute this one using norm INV. So it's a normal, inverse, and then the probability is this one, mean is 0.1, mu sigma is 0.1. Okay, then you see about 0.029. So which is similar with this chart here. So that is what we are trying to do here, right? So you want to draw a horizontal line, find the intersection point, draw vertically down, and then you see what is the value. So that is inverse transform technique. Okay, so having enough illustration or this explanation on this thing, then we know now how to generate this one, right? So basically this number is just like what we have here. So all the random number, you draw horizontal line of the CDF curve and then see vertically down what is the value. Of course, in this era, we don't really need to draw line on paper. So of course, it depends on the situation. If it is exam, then perhaps you need to compute using the formula, right? So if not, then normal distribution you can't integrate, right? I mean, you can't integrate directly. You still can do that like polar form and so on. But anyway, so there's no good way of closed form on integration of this thing. Okay, so but anyway, what you can do is that you can use the software. So norm inverse, and then it's basically this one. Okay, right, so then you can basically copy the formula for the whole column, then you get the value. Okay, so that is the inverse transform technique. That means given the CDF, what is the value of X that gives you the CDF, provided that you know the distribution. Okay, now that is some basic of this inverse transform technique on continuous random variable. If it is discrete random variable, things become a little bit more tricky. So let's look at this part here. Then we can say that, okay, now if let's say we were to write the inverse transform technique in slightly more mathematical form, right? So what we have is that we always say that fx, the subscript capital X here, refer to, we are looking at the distribution of X. Given the small x here is equal to the probability of X that is less than or equal to X, right? So that is the CDF. Okay, so what we have just now is that we are taking 0.24, right? Is equal to 0.24 is what we manually or randomly type into the example just now. Remember when we draw the horizontal line, that is 0.24 here, and then we say that, okay, Px is less than or equal to X. Okay, so our task here is basically to find what is X, what is the value of X, right? Okay, what is the value of X? Okay, so of course we are using some software. We say that, okay, we can use like norm inverse just now. Okay, so we use this function in spreadsheet and then we get, okay, we get the answer. Of course, in real life, in practice when you are working, you probably use software. In exam, you may want to do some integration depending on the distribution, right? So integration or summation. So that is for continuous. It's quite straightforward because continuous, the CDF for continuous random variable, right, is actually continuous. But a CDF for discrete random variable is actually non-continuous. So we take a simple example. Of course, we can always search online a lot of things here, right? So we search, like, for example, CDF for discrete random variable. So probably you will start to start to visualize what is this thing, right? So, but of course I can use Google, and then you can see that the chart here is a little bit okay. Right, so I just go into some random some of the website here. Okay, so you can see that the line is actually non-continuous. Okay, non-continuous is a step function because this is discrete random variable. So when you talk about continuous random variable, sometimes it's easier. Okay, right, so this is like a continuous random variable. You draw horizontal line, it will definitely touch the CDF line, and then you can draw vertically down, right? Let's see. Okay, so if you draw horizontally here, and then it touches the line, and then you can say, okay, go down. This is the x that you want. So that is the inverse transform technique. From the y-axis, you find out what is the x-axis, something like that. Okay, continuous is easier because it is continuous in the range 0 to 1. No matter where, as long as you start from 0 to, in between 0 to 1, you always touch the line. Okay, so no issue. But discrete random variable things become slightly different because you may not be able to touch the line. Okay, so sometimes, like for example, you draw like this. Okay, there's no line here, and but of course you can say that it should be here, and we will actually illustrate this thing later. Okay, but you can see that discrete random variable is slightly different, which is why we split it out and then talk about these things separately. Okay, so now let's go back to discrete random variable, and sometimes people do draw the CDF in this way. Let's find something like this, right? So it's a step function, so they will join vertically down, so that when you actually draw the line, so okay, this is a better illustration. Can I okay, right? So you can see that over here, if you draw a line vertically, horizontally, from here to here, you can touch the line. Now you can always touch the line. Okay, drawing in this way, then it allows you to touch the line. Of course, it depends on how do you define the range. Okay, so for example, if let's say it is like 0.8, so when you draw it down, it should be, is it this one, 4, and then when you get 1, then you get a 5. Not necessary, right? So this is something that we want to discuss later. So of course, in terms of inverse transform technique, we may not be using this one, but it's a good illustration that you can see a vertical line here. Okay, so you can also see something like this here. Okay, right, so like this one. So it's also a good illustration. So after 5, then no more. So basically x could be like 1, 2, 3, 4, 5. Okay, so let's look at this website. Probably you can see the what's that called? The distribution. Okay, so let's look at this one. Did they define this thing here? Okay, right. So you can see that like what we mentioned just now. So from 1 to 5, this is the density probability mass function, PMF, right? So when you draw the CDF, you draw it this way, then when you do inverse transform, you can always get the x. Okay, so for example, 0.9, you draw it here, then it touches here. This is 5, right? 0.9 is 5. So 0.4 is 3. Okay, so that is easy if you draw in this way. So you realize that it should be left hand included, right hand side is not inclusive, right? So when you draw the line, it should be like this. Of course, again, we won't draw the line here. So now, again, in a mathematical form, how do we illustrate this thing? So let me close this one first, right? So we don't really need the chart anymore. Okay, right, so now coming back to here, then if let's say you have px, let's say equal to xi, and then equal to probability of I. Just like just now, you have I equal to 1, 2, 3, 4, 5, right? So how do we do this inverse transform, basically you say that, okay, mathematically, then it should be like this. The value of x, it will be depending on what is it called, the random number that you generated. So x1, it will be equal to the first x if, let's say, u is less than or equal to p of 1. Okay. Okay, right, so what it means here, the capital U is the random number that you generate from the RAND function just now. So if, let's say, the first x1 is equal to 0.5, then you generate 0.3, then you say that, okay, this is x1, okay? So then other than x1, then for example, x will be equal to x underscore k, the kth number, if, let's say, we talk about CDF again, don't forget. So I equal to 1 until k minus 1. Okay. So summing up from I equal to 1 until k minus 1 of pi, it must be less than u that you generated, the uniform random variable, and it must be, this random variable must be less than or equal to, similar to this one. Where's the cursor? Okay, right, but it should be until k. Okay, so that is what we have here. Okay, so having this this part defined, right? So this part. So now we know how do we deal with the discrete random variable. So let's go back to the spreadsheet, and then of course I will put the screenshot here of the formula. Then we can actually look at this thing. So again, for discrete random variable, you may notice that, okay, sometimes you don't have, so all these are formula linked, you see, these are formula. Okay, so that's why every time the number is changing. So in order to get this 300 random variable, let's say now we define some random variable. So for example, the x, and then the px equal to x. Okay, so we can have px equal to x that is non-zero because this is discrete. If it is continuous, you notice that this is like right, so total probability must be equal to 1. So of course we can always check this thing. Right, so it's a 1. Okay, so now you have the first one, 0. Let me copy paste value first. So 0.91847. So what is this value? This is PMF, right? Probability mass function. When we talk about discrete random variable, this is PMF. Okay, right? So you can actually convert this to CDF, and then px less than or equal to x. Of course, this one is still the same number, and this one plus this one, right? So eventually it will become 1. Okay. Okay, right. So now you see 0.91847. So it's less than 1, greater than 0.5. So you say that this is, you see, it is greater than summing until 2, right? So it is greater than this one, but less than this one. So what it means here is basically saying this is a number 3. Okay, so 0.57154 is greater than this one, less than this one. So it's a 3 again, and then this is also a 3. So 0.03 is less than this number, right? So it should be x1, so which is 1. So x1 is not necessarily 1, 2, 3. It could be red, blue, green, something like that. But of course, when you talk about red, blue, green, it's quite hard for you to define like CDF of less than blue. So sometimes you don't do that. Okay. So 0.36703. What is this? This is basically like you see, comparing to this one greater, comparing to this one less than. So it should be a value 2. Okay. So that is some of the things that for discrete random variable, you can continue to complete this table, of course, for 300 values here. In order to make this thing using a formula in spreadsheet to do an inverse transform technique for discrete random variable, I will discuss this thing using VLOOKUP approximate matching in another video. So I will put the link in the description as well. Okay, so over here we understand, okay, so that is how the inverse transform works for discrete random variable. Okay, so that is simulation, and then now we just look at some of the simple example of simulation, and then before we end the video. So for example, if we have a fund value of 10,000 initially, so at the beginning of first year, this is at the beginning of second year, and so on, right? So now let's say I invest 10,000 in a fund, so some mutual fund or some stock market or anything. So we have the return, so next year it becomes 12,000, right? So in order to calculate how much I actually earn, I take what I have at the end of the year divided at the beginning of the year minus 1. So that is telling me that, okay, in the first year I earned 27%, and then of course I can continue to compute the percentages for all the years, right? So basically, like for example, this one, a negative value means that it drops in the value, right? So this one hash value cannot calculate it because it's a question mark here. Okay, so now the scenario is that I have invested for 10 years. So these are the 10 years of data, right? So I say that, okay, the return is around something like this. Okay, I may say that, okay, this is actually following a log normal distribution or following a normal distribution. It depends. Okay, so usually you won't say that this is log normal distribution anymore because you have some negative return, as you can see from here, right? You have some negative return. So you won't say that, okay, this is log normal distribution. But of course, it depends on how do you want to model this kind of situation, right? So this is in terms of return. But if we model it in something like this, instead of a percentages, we model it in like a multiplier. Okay, a multiplier. Okay, so from here to here the growth is 1.27, from here to here the growth is 1.05, and so on. So you can see that now when you have a decrease in the fund value is 0.97, so it's a number less than 1. So in this case, you know that it will definitely be non-negative. Then in that case, you can model it with log normal distribution. Again, there are a lot of situations or a lot of scenario when to use log normal and normal. Over here, we are just giving a very simple one. Most of the time, to be in fact, when you talk about return, most of the time you may want to model it with a normal distribution. Okay, so you will probably learn more about this thing in other subject, like for example, geometric Brownian motion versus arithmetic Brownian motion, right? So that kind of similar concept here. But over here, I'm just trying to do some illustration, so I use log normal distribution. So once you know that this is a log normal distribution, why is it log normal distribution? Basically, I generated column D from log normal distribution, and then I reverse calculate for, or reverse engineer for column C. Okay, so the purpose of simulation sometimes is we want to know what will happen in year number 11. So bear in mind, we are not talking about prediction here. So we sometimes want to know, like for example, what if the fund value drops half, and then what should I do, right? So in this kind of simple situation, you don't really need a model to run simulation because you have only one distribution. But a lot of times when you talk about, like for example, selling food, right? So you may want to say, okay, I have whether raining or not raining, right? And then let's say my business is like working as a food panda delivery, right? So then I say that, okay, the number of food delivery, right? So number of food delivery I can get is basically maybe 1,000, okay, 100 per day or 50 per day, depending on rain. Okay, sorry, this is not raining or raining. Okay, so depending on the weather. So in this case, if let's say you say that half chance, then you have only one sort of like distribution here. So this is like 0, 1, okay, binomial or Bernoulli, up to you. Okay, so over here, this 100 delivery is not necessary to be there, right? So we can say that, okay, this is the mean following normal with standard deviation, normal, mean with 100, standard deviation, maybe 20 delivery or 20 orders, right? So now I delete this one, I can change it to something like this. So same thing here, this one probably become 50 and plus minus like this. Okay, but if you use normal distribution, you can see that the numbers can go negative. Sometimes you don't want the number to go negative, and you may want to use like log normal. Okay, there are a lot more of distribution. I'm just using normal and log normal because we discussed these two only. Okay, so then you say that, okay, now I have like 1, 0 here, I have some variable here. So if I want to know today what is the expected value, then you see a bit different now, right? So 150, and then you need to consider this one. What if I want to consider the revenue instead of number of delivery? So like for example, my profit per delivery is following now the profit. I'm saying, okay, it's again it's like a log normal distribution. So I don't want it to go negative, so I always use log normal, but this is not the case when you are really modeling something in real life. Okay, so my profit is like $5, and then maybe over this standard deviation of 2, right, on the sigma of 2. Okay, so now you see I have 1, 2, 1, 0 here, I have 2 log normal distribution here, I have another distribution here every time I have this one. So in this kind of situation, when we want to say, okay, what is the expected profit I can get? That is a difficult question to answer directly. So simulation will help in this case. Okay, some other situation is like when you want to look at the percentile. We will talk about that in the last part of the video. Okay, so now this is basically one of the situation where you want to know. And of course, in this fund or portfolio return is sometimes quite straightforward. You don't really need simulation to deal with this thing. Okay, so like discrete case here, also same thing. You may want to say that, okay, I want to throw a dice for 1,000 times to test whether it is a fair dice or not. But okay, that one you have to, if you have the physical dice, you have to throw 1,000 times. But if let's say you just want to simulate the result of throwing an unfair dice, so what is how do we deal with that? Again, it is similar with like creating a table like this, and then you look at the random number, find a random number from uniform distribution, get the discrete number from using this technique. Okay, so when do we do this thing? Same thing here, back to this one, right? So instead of having like let me come back to here, 1, 2, 3, you may want to change it to rain or not raining. Okay, so if it is less than 0.5, you say that it is raining. If it is more than 0.5, you say that it is not raining, and then you can run the simulation. Okay, simulation, usually when you want to use it, you use it for a slightly more complicated scenario. Okay, so that is what we have here. In order to run this thing, like for example, how do we use a formula to get the numbers directly from the table? We will talk about that in a VLOOKUP video, which I will put the link in the description. So on how do we run this simulation for 1,000 times, 10,000 times, I will talk about this thing in another video by using VBA or without VBA, so to illustrate the process of simulation. Okay, so now that is the simulation part on what we want to do, things like that. Okay, so given basically is given the CDF, you want to find out what is the X here. So in other words, you try to simulate the scenario where what happens if the x is 0.1, what happens if the x is 0.3, and then you hope that eventually it will converge to the average, okay, so, or the expected value. For example, when you talk about like this continuous random variable, right, so given the column C, we find out what is column D, and what is the average here. Let us compute this one. Average of this column is 0.1024, right? So you see that it is actually quite close to what you have in the formula. The mean is 0.1. It's actually quite close already, given that this is only 300 simulations. So if you run this thing for 10,000 times, I believe this one will be even closer to 0.1. Okay, so that is what we expect the result to be. So sometimes you may think that, okay, if I expect the result to be the mean, then why should I run simulation, right? So because sometimes the situation is just too complicated for us to get what is the expected value intuitively or directly from the distribution. Like for example, this one, what is the expected profit? It would be involving, if you want to do some calculation, it will be involving quite some tedious calculation. In this case, you still probably able to do the computation. But in real life, if you are modeling a business model, financial statements and so on for a 5 years period, it's quite hard for you to do the calculation. So simulation is the one of the way, easier way. Okay, so now, of course, before we end, then the simulation here that we learn, can we use this thing as like a prediction? So basically, things to take note here is that a simulation is not a prediction, okay? So then why do we want to use simulation? This is because we illustrated this one here. Complicated scenario, you may not be able to obtain the expected value easily. Second thing, you may want to get a percentile, especially when you talk about, if let's say from insurance or banking point of view, you may want to calculate the reserve, the capital adequacy ratio and so on. Most of the time you need to deal with the percentile, okay? So strategic planning sometimes. So you run simulation, okay, so you can run like 10,000 times, and then everything usually is automated. So if X drop below, or for example, profit drop below 1 million, so we implement this strategy and then we see what happened. So sometimes it's a lot of assumption there, a lot of modelings, and the whole planning is actually quite complicated. Okay, so that is the video for this simulation. And then as we mentioned during the video, so there will be another video on how do we use VLOOKUP with approximate matching to do inverse transform method for discrete random variable. So continuous random variable, most of the times common one is already inbuilt in the spreadsheet, like normal distribution, you can use norm INV. Log normal, you can use log INV. Depending on the spreadsheet software that you are using, it could be slightly different, but it works the same. Okay, so that is the first thing. We will introduce another video on VLOOKUP with force, or well, with approximate matching to do this inverse transform technique for discrete random variable. And then we will have also another video on how do we run simulation using VBA or without VBA. Okay, so we will talk about a few different techniques, and then of course efficiency and so on. Okay, so of course for VLOOKUP, I will create another video for VLOOKUP as well for those is not familiar with VLOOKUP with exact matching. Okay, so that will be the end of this video. I will see you again in the next video. Thank you for watching. Bye bye.